Last time we saw that symmetric games can be represented with data structures that are far more compact than the payoff matrix, but it turns out that there are some types of games where we can be even more efficient. And among these, one of the most important classes is congestion games. The name congestion game arises from modeling phenomena like network congestion, where there can be an enormous number of users interacting and all trying to find the best ways to route their data. And in settings with thousands of players, writing down the normal form or even symmetric representation is completely hopeless. So the only way we can hope to analyze the game is if we can represent it compactly and compute equilibria using only that compact representation. And this leads us to the formal model of a congestion game, where we have a set of players and a set of resources. And for each resource, there is an associated congestion function. And that function tells us, based on how many players are using that resource, what cost each of the players using that resource will incur. And then a player's action corresponds to some subset of the resources, and then a player's utility is based on the sum over all of the resources that their action uses of the cost function evaluated at the number of players using that resource in the current profile. And this is a fairly general description. We can have symmetric players who all have the same action sets and incentives, or we can have different utility functions and different action sets for each player. And the actions may include all possible subsets of the resources, or only certain specific subsets. And the idea of a congestion cost gives the impression that the cost should be increasing in the number of users of a particular resource, but that's not necessarily required. So, to build some intuition for this formalism, we should think about what sorts of interactions we can model as congestion games. And a first example is a decision by a large number of people whether to attend a party. And the idea here is that attending the party gets better and better as more people are attending, until you cross some threshold where the party is too crowded, and then as more people are attending, it gets worse and worse. And we can model that decision by giving each player an action set that consists of staying home or going to the party. And we'll say that staying home gives a utility of 0, while going to the party gives a utility that is based on how many people choose to go to the party. So that means that the action that selects the party resource has a cost function that is described by an increasing function until we hit the capacity of the party venue, and then a decreasing function thereafter. In this case, the action and the resource correspond directly, and so when we count the number of players using the party resource, that corresponds exactly to how many players have picked the party action. And if the number of players choosing to go to the party is small, then the utility that each of them gets is the number of people at the party. But that only holds until we get to the threshold, and then each additional person who goes to the party lowers the utility of everyone who chose the party action. So if we think about the size of the representation here, well, I was able to describe the game by just listing these resources and their cost functions. But if we were to write down the normal form payoff matrix for this game, with, say, n equals 100, then our payoff matrix would have a dimension for every player of size 2, since they have 2 actions. And so we'd end up with a payoff matrix containing 2 to the 100 profiles. But since this game is symmetric, we could use the data structures from last time, where we saw that the number of configurations was players plus actions minus 2, choose players minus 1. And with 100 players and 2 actions, that comes out to 100, choose 99, which is 100. So the symmetric representation is exponentially smaller than the normal form representation, but we'd still need to store multiple arrays with those 100 configurations and their payoffs. And so our congestion game representation is still quite a bit smaller. But a much more interesting example comes up if we actually use a congestion game to model traffic congestion, where in this game we have n drivers who each have some starting point and some ending point that they are trying to drive between, and we have a graph representing the different roads that they could traverse, and then we could figure out for each of the roads, how does the travel time on that road depend on the level of congestion on that road, and use that to describe the cost function for each of the roads. And so the roads are the resources in the congestion game, but then the actions available to the players are different paths from their starting point to their ending point. So among the actions available to player 1 would be all of these different paths that I've drawn in red. And for whatever action they choose, their utility will be the sum over all of the resources that their action uses of the cost of that resource. So once every player has chosen some path, that gives us a profile, and we can use those paths to figure out how many people are on each road segment, and figure out the congestion cost for that road segment, and then each player's cost comes from adding up the congestion on all of their road segments. And since the utility is minus the sum of the costs, the players maximize utility by minimizing the congestion that they experience. And so if we ask for this game, how big would its representation be? Well, for the congestion game representation, we need to know the start and end point for all of the players, and we need to know the graph and the congestion function on each edge. But if we have those things, then we have all of the information to describe the incentives in this game. Whereas, if we were to represent this as a normal form game, well, first of all, this game isn't symmetric because the different players with different start and end points have different incentives. So we know we're going to end up with a big payoff matrix. But to figure out how big, we need to know how many players and actions there are. So let's suppose that we have 1,000 drivers in our model. So that gives us the size of the player set. But what about the size of the action set? How many actions are available to some player in this game? Well, for player I, their set of actions is the set of paths from their start to their end point. And if we tried to count how many paths are there from one node to another, there's an enormous number of branching points. We could go straight or left or right at the first intersection, and then here we could again go straight or left or right, and so on. And in general, the number of paths between 2 points in a graph can be exponential in the size of the graph. And so if our number of actions per player is exponential in the size of the graph, and the normal form representation is exponential in the number of actions, the payoff matrix for this game is doubly exponential in size relative to the congestion game representation that we have written here. So for a game like this, if we had to analyze the normal form representation, there would be absolutely no hope of finding Nash equilibria. But since the size of the congestion game representation is actually manageable, then as long as we can compute the equilibria using only the congestion game representation, we can actually analyze this model. So now the question becomes, can we analyze the model and find the Nash equilibria without having to resort to the normal form representation? And the answer is yes, because of a key theorem, which is that every congestion game has a pure strategy Nash equilibrium, and we can find that pure strategy Nash equilibrium by iterated best response. By iterated best response, what we mean is that we can start from any arbitrary strategy profile. We can pick any valid action for each of the players, and then, as long as there is some player who can gain by deviating, we'll have that player switch to their best response. We'll do this over and over again until nobody can gain by deviating. Obviously, that process does not work to find a Nash equilibrium in every game. Think, for example, of rock, paper, scissors. If we start from the arbitrary profile rock, scissors, then the player with scissors will best respond by switching to paper, then the player with rock will best respond by switching to scissors, and so on, and we'll just go around in a circle. So what we're saying is, for congestion games, we'll never end up in that sort of a cycle, and instead, computing these iterated best responses will always get us to a pure strategy Nash equilibrium. But to prove this claim, we need to think about another definition of potential games. A potential game is one where there is a potential function that we can apply to any profile, and that potential function, despite only outputting a single number for each profile, will capture all of the information about any player's potential deviations. So this function gives us a number for any profile, and if we compare two profiles that differ only by one player deviating, so here we're looking at one specific player switching from whatever is their action in profile S to the action A prime, while all of the other players are still doing the same thing they were in S. If we look at the difference in potential, that should give us the same difference as the incentive to deviate for the player who is switching. So if we look at the utility to the player who is switching to action A prime, and we take the difference in their utility when they switch versus in the original profile, that difference in utilities should be the same as the difference in potentials for those two profiles. And this is clearly not a thing that applies to every game, because most of the time you can't have a single number that captures everybody's incentive to deviate. Different players will have different preferences over the various profiles, and so it would be hard to capture everybody's incentives in a single number. And we also know that this can't be true of every game, because it's what we're going to use to prove that there is a pure Nash equilibrium, and we know not every game has a pure Nash equilibrium. But if you can come up with a potential function for every profile in a game, such that it has this property, then we'll show that means the game must have a pure Nash equilibrium that we can find by iterated best response. But first, let's actually describe a potential function for congestion games. Specifically, we'll show that every congestion game is a potential game by giving a potential function, which is the sum over all of the resources of the sum up to the number of players using that resource of the congestion function evaluated at that number of players. So importantly, this isn't just adding up all of the congestions all of the players experience. It's not just the social welfare. This inner sum goes from 1 up to the number of players using the resource. So when j is 1, we are adding the congestion when only one player uses the resource, and when j is 2, we add the congestion when 2 players use the resource. So we're summing up how much congestion there would be for each number of players up to the number that are actually using the resource in this profile. And so this is a function that we could evaluate for any profile, and we want to show that this function has the potential function property. Whenever somebody unilaterally deviates, their change in utility is equal to the change in potential. And in a congestion game, we know that every player's utility is a sum over all of the resources they are using of the cost of that resource. So when a player switches their action, all of the resources that were in the original action, they no longer experience the cost of that resource, but they now do experience the cost of the resources in the new action that they're switching to. And so their difference in utility will be the difference in these sums for the 2 resources. So when we calculate this difference in utilities, we'll get a difference between the sums for their new action and their old action. But I've written these sums wrong. Here I have just the number of players choosing the resource, but this should be the cost evaluated at the number of players. So let me fix that. So this is now the difference in utilities, but why is that also equal to the difference in potentials? Well, the potential is the sum over all of the resources of the sum of the congestion costs up through the number of players using that resource. And when we take the difference between these 2 potentials, any resources that are not being used by either of these profiles will appear in both sums and cancel out. And in this part, we'll be left with just the resources that are used by this profile, and then on the right, just the resources used by this profile. And on the inner sum, since only one player has changed their action, the upper bound of the inner sum will only have changed by 1, and so we will also cancel out all of the terms except for the last one in each of these sums. So all that will be left is the sum over the resources that their action is actually using of the cost to the last user in that profile, and that count, which is the last term in this sum, is the same as this count, since we're talking about the same profile. And so this expression also gives us the difference in potentials. So, because we referred only to the structure of a generic congestion game, this means that for any congestion game, we can write down this sort of potential function. And so now we want to show that any game with a potential function must have a pure Nash equilibrium. And that follows from the fact that the difference in utility corresponds to the difference in potential. If we start from some arbitrary profile and then have a player best respond, every time a player switches their action in their best response, they are improving their utility, and the amount of utility that they gain will be exactly the increase in potential from one profile to the next. And so, every time somebody best responds and switches actions, the overall potential will be increasing. And so there's no way we end up in a cycle where we go back to a profile we've seen before. We'll keep on going until we get to the maximum. And the profile that maximizes the potential has to be a Nash equilibrium, because if any player were to deviate away from that profile, they would be lowering the potential. And if you lower the potential, that means you're lowering your utility, which means you are not gaining by deviating. And so if the players iteratively best respond, they'll go to the maximum of the potential function, and that will be a Nash equilibrium. And so every potential game has a pure Nash equilibrium, and as long as we can do iterative best response, we can find that Nash equilibrium. So now the last question is, what does it look like to compute iterative best responses? Well, in the attending the party game, that just means letting each player decide, are they going to pick party or home? And so we can loop through all of the players and let each one make their decision. And if any of them changed their decision, then we'll loop again until everybody's happy, and we know that's a Nash equilibrium. For the traffic congestion game, starting from an arbitrary profile means starting from some arbitrary path for each of the drivers. So we'll have them each find some initial path from their start to their end. But now, once again, we will loop through the players and give each one a chance to best respond. In this case, a best response means computing the cheapest path from their start point to their end point, and that's a well-studied problem where we could apply Dijkstra's algorithm or dynamic programming or A-star search. And so each player, when it's their turn to best respond, will compute the cheapest path and pick it. And then once we've looped through all of the players, if any of them changed their path, we'll loop again and continue until nobody changes their path, at which point we know that we have a pure strategy Nash equilibrium. And at no point in computing that Nash equilibrium did we need to even think about the normal form representation or even enumerate all of the strategies available to a player, because the algorithms that find a cheapest path don't actually have to consider every possible path. The one thing that may be uncertain here is we don't know necessarily how many times we'll have to loop through all of the players and let them all best respond. We know that every time we compute a best response, we are improving the potential, but we don't know how much we are improving the potential by. And so it's possible that we'll be getting very, very small increments, and it will take many, many updates before we get to the maximum of the potential. But sometimes we can argue that it's never going to take more than a couple of rounds. And even in more complicated examples, running through this iterated best response is quite efficient in practice. And so whenever we can model the interaction that we're studying as a congestion game, that's great news, because we know there's a pure strategy Nash equilibrium, and we can generally find it way more quickly than we might first think based on the number of players and actions.